estimates. So this is the second webinar in my series of webinars which I was thinking to give on mineral inventory estimates and on its covering some essential topics on it. So going forward, this is me. I'm Dhruva Jyotinath, and I'm in mineral exploration and resource geologist, and I'm a member of OSIAM. A little bit of on housekeeping. All attendees are on mute and are requested to keep on mute. And if you have any questions, please enter it in the chat box, and we will answer it at the end of the session when the webinar will be completed. And if you are experiencing any technical glitches, please try exiting and rejoining the webinar. Hopefully that will get you a better connection. Disclaimer for this presentation. This presentation is compiled from the famous book Applied Mineral Inventory Estimation by Sinclair and Blackwell, which is readily available, easily available in websites and in internet and in hard copies as well. And it is only shared for knowledge enhancement and for informational purpose only, and should not be used and considered as professional advice or a professional service, although Data Code is always willing to engage with clients on any specific situations. Now, a little bit about Data Code. Data Code is a leading organization in the field of mineral exploration, groundwater, geotechnical engineering, and other allied geoscientific industries, bringing cutting-edge technologies and services to the industry. And we are in this market for now almost more than 25 years. The main disciplines which we cover are consulting services, training services, and data management, and also product sales. We have clients in exploration companies, mining companies, investors, and in government organizations. And these are some of the specialized services which I have mentioned here. So it's broadly data integration and analysis and targeting. We are also into management of geophysical and geophysical surveys, as well as we also provide end-to-end solutions in data management. Our co-partners are IDPX, which is a private limited company in India. Then PGW, it's more than 40 years of into consulting services or in geophysics, based at Canada. And there is another organization which is our partner is IGS, which is basically the commercial wing of British Geosciences based at UK. We have various business associations with the various research organizations like Manex CRC, and then we have various software organizations along with us, and various technical companies as well who are providing core scanners and various technological solutions to the geological problems and to the mineral exploration. Now, coming to the topic, some essential concepts of mineral inventory estimation. We will go through a little bit on its overview first. So as with so many professional undertakings, mineral inventory reports are filled with professional jargons, and there are a range of usage and not standardized everywhere. So it becomes very much useful and very much required necessity that you should be, or everyone should understand various specific terms which are used in the mineral inventory work. So today I'll try to cover some of those points, some of those concepts, some of those terms. So the topics which I am going to cover today is mainly from what is mineral inventory. Then I'll cover mineral inventory estimation. We'll give an example of mineral inventory estimation, how inventory estimation is done with a small example of 2D estimation method. Then the factors that are affecting that are very much important for actually realizing a mineral inventory. We'll cover some factors on. Then we'll go to the major topics like some essential topics like what is cutoff grade, continuity, what do you mean by continuity, reserves and resources, then something on dilution and selective mining unit, what do you mean by a selective mining unit, and some inlights on accuracy and precision. And then later on, ultimately, we will try to summarize all those 10 points, which I'll be covering today. Now, coming to the first topic, what is mineral inventory? Now, mineral inventory is basically a formal quantification of naturally occurring materials. Now, these are estimated by a variety of empirically or theoretically based procedures. And these are further divided into reserves and resources. And these reserves are basically inventories that are based on an economic feasibility study and are commonly classified as reserves. And those inventories that are less or less well established are considered as resources. Now, to give you an example of how a mineral inventory estimation is done or the process is carried out, this is an example of a figure. Here in this figure, you can it is a we are trying to show you how the reserve and resource estimates are done in terms of 2D or 3D estimations. So basically, reserve resource estimates are determined from a 2D or a 3D dimensional array of assay samples, and which is then applied to mineralized rock volumes. And then these mineralized zones or deposits are defined by geology is discretized by a number of blocks, which are commonly of uniform size, but it may not be necessary. And then this each block is then estimated using a nearby data within a search area of volume. So for example, here in this figure, if you see this black continuous line is actually the limit of mineralization, which is drawn on the basis of the geological informations. And that is actually discriminating or actually demarcating those black dots, which are basically the sample sites which are having some grades in it. And also it is bifurcating those white dots as well, which are having low or less or mineralization depending on the contact, which on the basis of which the contact has been drawn. So, and then further, this mineralized has been discretized by array of blocks, and these array of blocks are used for further used for resource estimation. For example, this particular block, which is having which is estimating within this circle all the samples or all the sample site locations which are falling within this circle are used for estimating this particular block. And in similar way, the estimations are done for each of the blocks, and then it gets aggregated and the proper block estimation is done. So this is a short example of how actually resource estimation is done and what is the process of mineral inventory estimation. Now coming to the factors important for realizing a mineral inventory. Now the very much first step and of understanding a mineral inventory is to first understand when the life of a mine actually starts. Now it is not the day when the production is starting actually, but when the company sets out to explore for a mineral deposit, that is the day or the time when actually mineral estimation starts. Now there is time and money is spent looking for or locating or quantifying a promising mineral occurrence. And also it is not unusual to spend 5 to 10 years searching for a mineral deposit, and then also it may result that we may not find any particular deposit, or not many of the ones that are found will have that potential to become a mine. Now, as I said, the investment necessary is to start a mine is huge, and it is in the orders of tens to hundreds of millions of dollars. And for that investment to be profitable, the potential product or the mineral deposit which we are looking for in the ground must be present in adequate quantity and quality to justify a decision to invest. So then comes the mining and processing systems, which is required to extract those products. And those systems can only be incorporated or only be installed if those can get operated in such revenues that which can offset these investments to provide an acceptable profit margins. So overall, you can say that all technological and financial decisions that are required regarding plant production or building and or understanding the mineral assets available are very much important. Like the estimation of grades is quite important. Location of material in the ground, the in situ resources must be known with some acceptable degree of confidence. Then also mining profits are broadly and strongly leveraged to the product price and the realized grade of the material that is mined. So for a small difference between the planned or the estimated and the realized production, it can impact the mining profits. Even a small change in the metal price can have a large impact on the mine profitability. So these are some of the factors which needs to be kept in mind when we are looking for a mineral inventory or estimating a mineral inventory, and for ultimately for profits. Now let's deep dive into some major topics or major concepts or major terms rather which are used in mineral inventory. So we will start with ore. Now in general, ore is defined as a valuable solid mineral that is sought and later extracted from the workings of a mine, and that is expected with the hope that is going to give an advantage to the mining operator as well as to the community as a whole. But this general definition doesn't fit much into the realistic understanding of mineral inventory estimations. So in terms of mineral inventory estimation, there are some specific definitions for an ore. The term ore is applied in mineralized rock in three major senses: a geologic and a scientific sense. For example, with a view of a geologic context, an ore can be defined. Then there is quality control in ore reserves. When you're defining an ore reserve in an economic point of view, then there is quality or the grade of the material is also important to identify, and on that basis ore is defined, ore can be defined. Then also for broken or mineralized ground in a mine, for example, there is already an existing mine and there is some broken material, which regardless of the grade which is there in the mine, in the production area or in the ore zone areas, that can be considered as ore as well. But for mineral inventory work, the second definition is of more importance because that implies basic distinction between an ore and an waste. So basically, in short, if you want to say that what is an ore, by that is any material which is mined at a profit as ore, and any material which is containing insufficient value to earn a profit is waste. So that's the clear definition of an ore and waste. Now to summarize the definition of the ore component, the ore component of a particular mineral deposit is function of time factors. So basically like metal price, technology, tax regime, which can change with time. Then it is also a function of place factors like the relation to infrastructure, where your infrastructure is and where the deposit is. So that's the place factor also comes into picture when defining an ore. Then the legal factors like environmental licenses or the labor laws, the safety of all the social factors around that deposit also gets implied when we are defining an ore. And obviously the profit and the discount rates, which are the financial terms, that is also is used as a function for defining an ore. Now, for example, in general, mines are put into production with the understanding that there will be an acceptable return on the necessary investment, but circumstances may dictate significant changes to the foregoing philosophies or the policies, and the concept of profit margin can change over time. A mine might operate at a loss for reasons of tax advantage, long-term planning, or and in anticipation of short-term changes in the metal prices or product sales. There can be government reasons as well, like government may impose regulations or incentives that affect operations that normally expected to create losses. For example, historically, there is a case in South African gold mines and the Alberta tar sands that some material was mined at a loss because it would otherwise would not be recoverable or perhaps would had been lost forever. So there can be various reasons, and while all the factors or the functions which needs to be taken care of while defining an O component. Now, recognition of ore and waste. The recognition of ore involves the consideration of three different categories of profit. The first is that relating to the small increments of ore. The second one is that referring to annual or other periodic outputs of ore. And third is that expected from the entire ore bodies. Now, it is to be noted that for each of these types of profit, there is a different corresponding threshold that separates ore and waste. Now, this corresponding threshold is nothing but which we call as cutoff grade, and which is the next topic of our discussion today. So about something about cutoff grade. A cutoff grade is a grade below which the value of a contained metal or mineral in a volume of rock does not meet or certain specified economic requirements. Now, cutoff grades are used to distinguish blocks of ore from waste at various stages in exploration, like during exploration, it can happen during development, there can be different cutoff grades. During production stages, there can be different cutoff grades. Now, this ore and waste selection is based on estimates, which is obviously containing some error, rather than on true grades, which are actually unknown, and it will be known only when you actually produce or you open up the mine. So this brings us to another two categories of cutoff grade, which is estimated grade and a true grade. Now, an estimated grade, as I said earlier in this slide and in the previous slide, that estimated grade is basically the estimations is the grade which has came out through the estimations of the mineral inventory. Whereas the true grade is something which is there in the ground, which we can realize only when we have opened it and produced it and bring it at the surface or at the milling locations. Then only we can identify what is the true grade of that particular block. Now, here's an example which is shown, not an example, it's a graph which is shown of true grade versus estimated grade. It's a plot of estimated grades versus true grade and of some particular block. So these dots are basically grades, average grades of average estimated and true grades of particular blocks of mining. And we applied a cutoff grade, for example, at 0.2% for true grade and 0.2% for estimated grade. And then when we extend this to lines, it forms four quadrants. The quadrant one, you can see here, this quadrant one is basically it's belong to ore blocks which are correctly classified as ore, because you can see it is above true grade as well as above estimated grade. So it's basically the ore blocks which are correctly classified as ore. Now, when you come to this quadrant two, it's basically quadrant two. Here you can see it is basically the ores which are incorrectly classified as waste, because the estimated grade of these blocks in quadrant two are less than the cutoff grade, whereas the true grade came out to be higher than the cutoff grade. So these are the ore blocks which got incorrectly classified as waste. Then when we come to this quadrant 3, you can see waste blocks which are correctly classed as waste. So these are having lower estimated grades as well as lower true grade values. And then when we come to quadrant 4, there are some blocks which are actually classified as waste, but they are having some which are actually incorrectly classed as ore rather, and but are actually in true grade sense they are actually waste. So that is how this plot can be understood, and so this brings us to that fundamental concept that an estimate can never met the production scenarios, or can never met the production. There will be always there will be some conditions where some ore will be lost or incorrectly classified as waste, and there will be some ore that is recognized and is diluted by waste or incorrectly classed as ore. So if you see in this plot again, and if you draw a regression line through that data, then this also indicates the common result for any polygonal estimates. Like on average, estimates of high grade values are always going to be overestimated, are always going high values are generally overestimate the true grades, whereas if you talk about the low values, the low values generally underestimates the true grade. and and estimates are produced. Otherwise, uh, the first scenario is quite common when the higher values gets overestimated and lower values gets underestimated. Now, to summarize this understanding of cutoff grade, in the case of block estimation, it is evident that some O blocks will be inadvertently classed as waste, which is quadrant 2 in that previous figure, and some waste blocks will be classed erroneously as ore, which is quadrant 4 in previous figure. Now, the volume of a predefined mining unit on which mining selectivity is based and to which a cutoff grade is applied can change during evolution, as well as the cutoff grade can change by itself depending on the time. Now, as the cutoff grade increases, the tonnage of the ore will decrease and the average grade of that tonnage will increase. As a rule for any stripping ratio, which is the units of waste that must be removed for each unit of ore mined, this increases with the increasing cutoff grade. Now coming to another topic, which is continuity. Now continuity is the state of being connected or unbroken in space, as per English dictionary definition. But Sinclair and Well in their book Applied Mineral Inventory Estimation, they try to define continuity in two types, which is one is geologic continuity and another one is value continuity. Now, when we talk about geologic continuity, it is basically spatial from a geometric or physical feature such as mineral deposit or a mineral domain. There can be primary continuity, geologic continuities like veins, mineralized shear, mineralized stratums, and there can also be secondary geologic continuities like post mineral faults or some structures developing through metamorphism or through folding or sharing of deposits. Now, when we talk about value continuity is basically spatial distribution features of the quality measures like grade values or the thicknesses of the horizons or the ore zones. So that's a value continuity. Sorry, I think I got disconnected for a second or so. So maybe when I talking about value community continuities, that is basically spatial distribution of grades and the thicknesses. Now, to understand this continuity, there is various distinction between the two types of continuity, and that can be appreciated by some particular simple examples, like for example a vein. When you talk about a vein, which is a continuous geologic feature, so that's a geologic continuity, and within that vein, if you have some ore shoots which are basically continuous in terms of some grade horizons or grades, numeric grade values, then those ore shoots or those zones are, you can termed as them as value continuity. Now, it is very much important to understand both these types of continuity because because it will help in appreciating the implications of each in the estimation processes, because there will be implication of a geologic continuity as well as value continuity when uh, we do any mineral inventory estimations. Now, for example, here in this figure, the impact, what it is an illustration was shown just to show the impact that an error in interpreting a geologic continuity can have on the mineral inventory estimation. Like for example, in this figure, you can see earlier the geologic continuity was made through this dotted line, and the ore body or or the vein was considered as a continuous vein. But when most informations came through and with the incorporations of structural data, structural informations, it get divided into four shared veins. So that is the impact of information and data, which can impact the geologic continuity and the value continuity and ultimately to the mineral inventory estimation processes. Now let's go understand further little bit on reserves. What is reserves and resources? Now a mineral inventory is commonly considered in terms of resources and reserves. Now, this definition currently vary from one jurisdiction to another, although there are some increasing efforts which are being directed towards internationally accepted definitions. International organizations like CRISCO, Competent Committee for Mineral Reserve International Reporting Standards, are aiding countries to develop some principle-based reporting codes. Currently, CRISCO has almost covered all through the world, and uh, uh, jointly with those different countries, they have formed a different guiding principles for reporting of resources and reserves for each country. Like for India, it is through NACRI, the EMIC code has been introduced by CRISCO, which is in line with the international reporting standards. Like for Australia, it is JOC, Code of Reporting. For USA, it is SME. And then for Canada, it is CIM, ICM codes of reporting, which is called NI 43101. So similarly, it is trying to cover all through the countries and putting their efforts to have a principle-based international reporting code. Now coming to the definitions of resources and reserves. Now a resource is an in situ, that is on surface or underground mineral occurrence that is quantified on the basis of geologic data and geologic cutoff grade only. And when we talk about the O reserves, it is used only if a study of technical and economic criteria and data relating to the resource has been carried out and is stated in terms of mineable tons or the volume and the grade. Now, when we talk about resources and reserves and further when we are talking about reporting those resources and reserves in public domain or in a public release, another important term or another important uh, concept, or not a concept, another important term which is very much important, critical to understand, is the role of a competent person. Because for reporting any mineral resources or reserves in public domain or in public release, for any international code of reporting, you require a competent person who is actually going to sign on those reports and who is actually going to report those resources in the public domain, resources and reserves in the public domain. Now, a competent person is a mineral industry professional. He can be a member of any member or fellow of any recognized professional organizations like OSIM, AIG, SME, CIM, Geological Society of London, etc. There are many other organizations as well. And these organizations have enforceable disciplinary processes, including the powers to suspend or expel a member. But there are different levels of experience required, which varies for different international codes, like under CRISCO, which like JOC has different criteria of experience required for a person to be a competent person. Similarly, SAMREC, NI 43101, or SEC, or IMIC even for India have different criteria for a person to become a competent person. Now, coming to the classification of resources and reserves in terms of this CRISCO template, this is the figure which is there in the CRISCO template, which is basically dividing the mineral resources into inferred, indicated, and measured, and mineral reserves into proved and into probable and proved categories, with increasing geological confidence, and also considering all the factors which are called modifying factors like mining, processing, metallurgical, economic, and marketing factors. So if you remember in my last webinar, I have shared one slide for a layman understanding that with a fishing tail, how resources and reserves can be understood and what is the role of modifying factors. So if you remember, I mentioned that if you thought of a fishing tail and you went out for fishing, so when you are thinking of a fish that is an inferred category, you don't know what is the resource, what type of fish you are going to extract or going to catch. And then when it comes to your table as a dish, after preparing it through cutting it and preparing it, when it is coming as a dish, it's not only the fish which is there in the dish, there are some add-ons as well, like spices, vegetables, which is actually completing that dish. And these spices, vegetables, knife are nothing but the modifying factors, and that dish of fish is your proved category of mineral of resource. So that is how you can understand the implication of or understand the growing confidence of from resources to reserves. Now, the basic question here is why are mineral resources and ore reserves are classified? Now, it is basically to enable users of the estimates to make informed, even the investors to be make informed decisions regarding the relative risks. It does not need to be a very much complicated process, but what it requires to reflect the competent person's view on the deposit, which is much critical. Now, understanding resources and reserves. So prior to any mineral inventory estimation, there is a variety of exploration or information there is a variety of exploration information which is available. Now, as exploration continues and advances, this information base increases. And when this information base increases, the level of detailed knowledge of that particular deposit also increases. And ultimately, the estimates of it gets impacted on the estimates of resources and reserves, because these estimates and resource and reserves then gets depended on these continuously changing data, and these continuously changing data keeps on continuously improving the geologic interpretations derived from those data sets. And when we talk about these type of data sets, these data sets can be broadly divided into three major categories, like location data sets, geologic data sets, and sampling and assaying data sets. Now, in terms of location data sets, there can be surveyed maps, cross sections showing locations of geologic control, mineral map showing drill hole locations and orientations or core orientation data, exploration pits or underground workings. These can be location data sets, which is actually improving the confidence on the mineral resource estimation process. The geologic data sets includes detailed geologic maps and sections showing rock types, structural data, alteration, mineralization types. It can be a description of supporting geochemical and geophysical survey data and interpretations. It can be factual data distinguished from interpretations. And then there are many other things, like the impact of cutoff grade can also be a geologic control. Then the mine designs include effect of mineral prices. These can be some other impacts of data sets which can impact the mineral resource inventory estimations. So in terms of sampling and assaying, it is basically a description of all sampling methods, which includes quantification of sampling variability, sample descriptions, sample reduction, then procedures and their adequacy, bulk sampling designs, results, and their duplicate sampling. So these are the sampling and assaying data points or data types, which also improves your mineral resource or mineral inventory estimation process. Now, when we are talking about reserves, there is another important point or another important topic or concept which needs to be understood, which is feasibility study. Because for any common for any common process, if you want to progress from resources to reserves, it has to be done through a feasibility study, and it is internationally accepted. Now, what is a feasibility study? It is basically covers a broad range of project evaluation procedures that yields detailed insight into the geologic and quantitative database, also the resource and reserve estimation procedures, then production planning, mining and milling technologies, and then operation managements, financing, and environmental and legal concerns. So these all topics needs to be covered or understood or analyzed and evaluated properly for the risks, and that gets included in the feasibility study. Now, if we want to summarize all what we have learned in terms of resources and reserves, so basically it starts with exploration information, and with the increase in exploration information, it first permits estimation of resources, and then eventually estimation of reserves of different categories comes into picture. Now, when we talk about reserve resource estimation, it is continuously changing with increase in continuously improving database. Further, for classifying reserves, we apply feasibility study, which is basically evaluation to determine if the profitable mining of a mineral deposit is actually possible or not. That's all in about resource reserves concepts. And now we move into another concept, which is called dilution. Now, what is dilution? Dilution is the result of mixing of non-ore grade material with the ore grade material during production, and with generally leading to an increase in tonnage and decrease in mean grade related to the original expectations. Now, a conceptual discussion of dilution during various mining operations is provided in this figure in the right hand side, which is after Alborod in 1994. So you can note that at every stages there is some ore which is lost and some waste is getting included, and this is what happens. And in any when we go into production of any ore deposit, and it is a fact, it will happen, the dilution will be there. Now, dilution can be broadly divided into two terms, two types of dilution, which are internal dilution and external dilution. When we talk about internal dilution, it is basically low grade material surrounded by high grade material, and whereas external dilution is low grade material marginal to high grade material. Internal dilution are further subdivided into two types, which is sharply defined geometric bodies and then inherent dilution. Whereas in case of external dilution, it is basically sloughing of walls, difficulty when there is difficulty of sorting in open pits, or there is inadvertent or purposeful mining of barren or low grade material at the margin of an ore zone. Now, coming to internal dilution, the two types of internal dilution, geometric internal dilution actually results from the presence of a well-defined waste bodies within an ore zone. For example, barren dikes cutting the ore zone, it can be an geometric internal dilution. Then inherent internal dilution results from the decrease in selectivity that accompanies an increase in the block size, that is resulting from loss of equipment digging selectivity, used as the basis for discriminating ore from waste, even where no entirely barren material is present. So, for example, if you have a machineries which is of a particular size, and that is will be there for the mining purpose, then there will be some internal dilution depending on the size of the ore and the size of the machine. And similarly, there can be internal barrens within the ore zones, which is its inherent property. And when you're selecting the block size, that waste materials are coming into your for geometric reasons or for mining purposes, you have selected some dimensions of the ore which you are going to extract from the deposit, and for selecting those dimensions you are adding some waste materials which you have to mine because to keep it geometrically correct or geotechnically correct, for example. Then these are some inherent internal dilutions which will be there. Now, when we talk about external dilution, it is basically in terms of if we talk about underground mining, it's basically when there is a stope, when the stope walls physically fall while extracting those mines, extracting that stope. So in that case, these external dilutions may happen, and that may happen because of the rock properties. The rock material can be loose, or also maybe because of the widths of the ore, which is quite less than the minimum mining width which is available. Now, external dilution can be somewhat less significant in case of when the deposits are quite large or there is some gradational boundaries. in comparison with the small deposits. It is because the diluting material in case of large deposits or where there is gradational boundaries can be very small and proportion to the actual mine tonnage, and also the contained metal, it may contain those diluted materials may contain some metal as well, possibly near to the cutoff grade because of the gradational content. So in general, in some certain proportion of waste must be taken along with ore during the mining operation. That is quite often, and it has to be there when we are talking about planning and mining an ore deposit. And so there will be some dilution. This form of dilution can be impossible to estimate with confidence in advance of mining, but experience is probably the best judge. People get experience. The mining geologists, the mining engineers get experience with their day-to-day activities, and this growing experience helps them to identify the dilutions in improving those dilutions and getting extracting more ore out of the deposit. Now there are some accepted procedures for estimating dilution in underground as well as in open pit mining, which you can which are for operations, and there are various referred books available online, and if you email me, I can also share some articles on dilution, understanding dilution, or the accepted procedures which are required for estimating dilutions. Now coming to the next topic, which is selective mining unit, SMU. Now this selective mining unit is the smallest block on which selection as ore or waste is commonly made. Now the size of an SMU generally is determined from the constraints associated with the mining method to be used and the scale of operation that is required. Now for design purpose here, for example, this small block is considered, these small blocks are considered as the smallest mining unit in the three-dimensional array for estimation purpose, and is used. Now this three-dimensional array of SMU is commonly the fundamental basis for any feasibility studies, which then implies to classification of reserves. Now hence SMUs are normally the minimum volume for which actually you are estimations are required. And in a particular situation, an SMU could be the volume of broken material in a single truck that is directed to either to a mill or to the waste dump, depending on the assigned grade. Now, this selection of an SMU is also critical to mineral inventory estimation because it can be the basic unit classified. First, it can be used for as a resource classification, for classification into measured, indicated, or inferred. And then second, it may be possibly as a reserves for proved and probable. So consequently, the dimensions of an SMU must be determined carefully. Those dimensions depend on such interrelated factors such as the probable blast hole spacing during production, specifications of mining equipment, bench height, and the blasting characteristics of the ground. Now coming to my final topic, which is accuracy and precision. Now, when we talk about accuracy, it is nearness to the truth, and significant inaccuracies can produce identifiable biases and departure from a true value. Now, precision is a measure of reproducibility of a result by repeated attempts. It is possible to have good reproducibility and poor accuracy, so both must be considered in detail. Now, when we talk about potential sources or significant sources of errors in the estimation or in the mineral inventory, it is basically the sampling. There can be sampling error. There can be analytical error, which is basically including subsampling errors. There can be some estimation errors like error made in extending the grade of samples. The example I showed to you about the estimation of selecting a circle, so that identification or selection of that circle can also impact the errors in the estimation processes. Then there is bulk density, which is too often we generally consider that assume that the bulk density of mineralization remains constant, but it is not necessarily actual. Bulk densities can change of a deposit throughout a deposit. Then there can be geologic error. When we talk about geologic error, basically errors in the assumption of the ore continuity and the geometry of a deposit. Then there can be some mining method not adapted to the geometry of the deposit, that is selectivity of the ore and the waste that is not optimal. Then there can be variable dilutions from surrounding wall rocks. Human error can be there, like misplotting of data, misplaced decimals, and finally there can be some frauds. It's not happen commonly, but you can't avoid that as well. There can be some salting or substitution of samples or non-representative data, etc. Now, the implications of such errors results in inaccuracy and in imprecision. These factors can lead to both inaccurate estimates and imprecise estimates. Inaccurate results can be obtained very precisely. For example, if a bias or systematic error is inherent in any one of the sampling procedures, the analytical method or the data selection procedure can get impacted. Regardless of how accurate assays or resource or reserve estimation processes are there is some level of random error which will prevail in data for or in estimates that we have to understand. Now, to summarize, errors in mineral inventory estimates are not entirely quantifiable. There are obvious estimation errors that arise because a small sample is used to estimate a large volume. In addition, however, there is potential for very large error arising from the uncertainty of geologic interpretation of the geometry and the internal continuity of the ore. Hence, it is very much important to be precise and in mineral inventory estimations than to be accurate. So that's all I had in today in my all the 10 topics. So let's summarize what we have gone through in today's webinar. So we understood about the mineral inventory estimation, which is basically a formal quantification of naturally occurring materials. Then we learned the basics of estimation and block modeling with an example of 2D estimation process. We have gone through the factors important for realizing a mineral inventory, like when life of mine actually starts, the amount of time and money that is spent for discovering a mineral deposit, the necessary market and technical factors impacting the mineral investment and acceptable profits. Then we learned about some important terms used in mineral inventory and mineral industry, like ore, what is waste, what is the cutoff grade, what is estimated grade and true grade, the geologic continuity and about the value continuity. We understood that resources are quantified in ground mineral resources occurrences, whereas reserves are the part of that in-ground material which is technically and economically feasible to mine. Understood that the increase in exploration information first permits the estimation of resources and then eventually the estimation of reserves. These reserves and resource estimations are continuously changing in response to improving database. And we also understood that reserves are defined by a techno-economic studies called feasibility study, which is basically evaluation to determine if the profitable mining of a mineral deposit is possible. We have gone through the examples of the information base required for mineral inventory study, which are divided into location, geologic, and sampling assaying data types. We also learned that there are two categories of dilution, internal and external. Then we understood about a little bit about the smallest mining unit, SMU, which is normally the minimum volume for which estimates are required, and the dimensions can depend on various interrelated factors like probabilistic blast hole spacing during production, specifications of mining equipment, bench height, blasting characteristics of the ground, and finally we have gone through the accuracy and precision. So with that, I conclude my my session, and you are welcome to ask any questions. You can type the questions in the chat box, or you can unmute yourself and ask the questions as well. Thank you and happy learning. So if you have any queries, we can go through the queries. I think our session is going to end at 12, so we have 5 minutes. So if there is any queries, you can ask, or maybe you can also contact me at my ID, or you can contact DataCode for any further queries as well. So there is a question, how to define dimensions of SMU. So basically, when we are talking about dimensions of SMU, so we have to first understand what an SMU is, which is, I try to let you get you understand through this particular slide, that basically it's a three-dimensional uh, block which we are considering. Now this depends on the two things. First, when we are doing an estimation, this depends on the drill hole densities as well, in which we are going to estimate. And secondly, it is the most important part of identifying an SMU is the mining parameters, or the mining size which we are actually going to carry out for a particular mine. So for example, if we are in an underground mining scenario, what is going to be the stope size of for a particular mine or for a particular blast? So that becomes my smallest mining unit. The amount of material, or the shape of the or size of the dimension which we are considering for actually blasting a material out through a particular single blast, these dimensions becomes our smallest mining unit, and on that basis we should be identifying our smallest mining unit, and then we should be carrying out the estimation process while reserve estimations. Now, second question is, how does value continuity help to estimate mineral inventory? Now, when we talk about value continuity, basically we are talking about grades, like they can be copper grade, lead, zinc grade, or any aluminum grade. So, or we are talking about thicknesses, so which are continuous. So any value which is continuous and is a numeric value, are basically are considering them as continuous data sets. Now, for example, when ultimately why we are here in this mineral inventory estimations, because we want to identify some ore which is ultimately going to be mined, and if some deposit is, or is particular geological shape is a ore or not, it is getting classified by that the grade value which is there in that ore. Now this grade value is always a continuous value, and if, for example, when we talk about cutoff grade, we are considering say 0.2% cutoff grade of copper. Above 0.2% of copper cutoff grade is going to be an ore. Then we are identifying a value continuity added to it, for which is actually the point greater than 0.2% copper, and these values are actually defining my continuity of the ore bodies, and which is ultimately defining my ore, defining and helping in my in mineral inventory estimations, because ultimately these grade continuity or the thickness continuity are going to define the type of mining methods, are going to define how much value I am going to generate in terms of profits or in terms of revenue from that ore deposit. So I hope I could able to make you understand. Otherwise, I'll share you some further notes if you require. You can email me and I'll share some further notes, or we can discuss it further in detail for understanding this continuity. There is a whole chapter of understanding geologic and value continuity, and maybe I will try to cover it in some webinars only covering what is geologic continuity and what is value continuity. So thank you for your uh, presence and listening to it. Please provide the feedback. My teammate has shared a link, which in the chat box you can provide your feedback through that. And we will be also publishing the recorded session of this into our DataMine site, into our YouTube channel, as well as in the LinkedIn. And thank you. And in these pandemic